Boolean Algebra, Lattices. Welcome friends. In an earlier chapter, we have gone through the topic partially ordered sets or posets. Let us now continue with the topic and describe what a lattice is in this chapter. Since you are familiar with the basic concepts, we will move on to the topic without much introduction. Lattices and algebraic structures. A lattice is a poset A less than or equal to in which every subset AB consisting of two elements has a least upper bound LUB and a greatest lower bound GLB. Lattice structures often appear in computing and mathematical applications. For example, Figure 1 shows a lattice. There is a natural way to define an algebraic system with two operations which define a lattice. Let A less than or equal to be a lattice. Then we define an algebraic system A join meet, where join and meet are two binary operations on A. We denote LUB of AB by A join B and call it the join of A and B. Similarly, we denote GLB of AB by A meet B and call it the meet of A and B. We shall refer A join meet as the algebraic system associated with the lattice A less than or equal to. We shall also denote plus or dot for join and meet respectively. Here is an example. The algebraic system for the lattice given in Figure 1 is shown in Figure 2. So, in the first table you can see the join operation of the elements A, B, C, D, E, F, G. For example, A join A is A, B join B is B, C join B is A, etc. And in the second table you can see the meet operation between the elements A, B, C, D, E, F, G. For example, B meet C is equal to E, etc. Example 2. Let S be a set. Consider P of S, which is the power set of S. As we have seen, the subset or containment is a partial order on P of S. Let A and B belong to the poset PS with containment. Then A join B is the set A union B and the element A meet B is the set A intersection B. Thus, P of S is a lattice. If S is the set ABC, the lattice P of S with containment is shown in Figure 3. Example 3. Consider the poset Z plus with less than or equal to, where for A and B in Z plus, A less than or equal to B if and only if A divides B. Then Z plus with less than or equal to is a lattice in which the join and meet of A and B are their least common multiple and greatest common divisor respectively. Thus, A join B is the LCM of AB and A meet B is the GCD of AB. Example 4. Let n be a positive integer and let Dn be the set of all positive divisors of n. Then Dn is a lattice under the relation of divisibility as considered in the previous example. Thus, if n is equal to 20, we have D20 is equal to the set 1, 2, 4, 5, 10 and 20. The Hasse diagram of D20 is shown in Figure 4. If n equal to 30, we have D30 is equal to the set 1, 2, 3, 5, 6, 10, 15 and 30. And the Hasse diagram of D30 is shown in Figure 5. Example 5. Which of the Hasse diagrams in Figure 6 represent a lattice? Here in this figure, we can see Hasse diagrams A, B, C, D, E, F and G. The solution is the Hasse diagrams A, B, D and E represent lattices. Diagram C does not represent a lattice because F join G does not exist. Diagram F does not represent a lattice because neither D meet E nor B join C exist. Diagram G does not represent a lattice because C meet D does not exist. Sublattice. Let A less than or equal to be a lattice. A non-empty subset S of A is called a sublattice of A if A join B is an element of S and A meet B is an element of S whenever A and B belong to S. Example 6. Consider the lattice L shown in Figure 7a. The partially ordered subset SB shown in Figure 7b is not a sublattice of L since A meet B is not an element of SB. The partially ordered subset SC in figure 7c is not a sublattice of L since A join B is not an element of SC, but we can see that SC is a lattice when considered as a poset by itself. The partially ordered subset SD in figure 7d is a sublattice of L. Isomorphic lattices. If F from A1 to A2 is an isomorphism from the poset A1 less than or equal to 1 to the poset A2 less than or equal to 2, A1 is a lattice if and only if A2 is a lattice. In fact, if A and B are elements of A1, then f of A meet B is equal to f of A meet f of B, and f of A join B is equal to f of A join f of B. If two lattices are isomorphic as posets, we say that they are isomorphic lattices. Properties of lattices. Before proving the properties of lattices, let us recall the meaning of A join B and A meet B. First one, A less than or equal to A join B and B less than or equal to A join B, where A join B is an upper bound for A and B. Second one, if A less than or equal to C and B less than or equal to C, then A join B is less than or equal to C, where A join B is the least upper bound of A and B. Third one, A meet B is less than or equal to A and A meet B is less than or equal to B, where A meet B is the lower bound of A and B. If C is less than or equal to A and C is less than or equal to B, then C is less than or equal to A meet B, where A meet B is the greatest lower bound of A and B. Theorem 1. Let A less than or equal to be a lattice. Then for every A and B in A join B is equal to B if and only if A is less than or equal to B. Second one, A meet B is equal to A if and only if A is less than or equal to B. And third one, A meet B is equal to A if and only if A join B equal to B. Proof of first part. Suppose that A join B is equal to B. Since A is less than or equal to A join B, which is equal to B, we have A is less than or equal to B. Conversely, if A is less than or equal to B, then since B is less than or equal to B, B is an upper bound of A and B. So, by definition of least upper bound, we have A join B is less than or equal to B. Since A join B is an upper bound, B is less than or equal to A join B, so A join B is equal to B. The proof of part B is analogous to the proof of part A, and the proof follows from part A and part B for part C. Theorem 2. Let A less than or equal to be a lattice. Then the idempotent properties A join A is equal to A and A meet A is equal to A. Second one, commutative properties A join B is equal to B join A meet B is equal to B meet A. Third one, associative properties A join B join C is equal to A join B join C, and A meet B meet C is equal to A meet B meet C. Fourth one, absorption properties A join A meet B is equal to A and A meet A join B is equal to A. Theorem 3. Let A less than or equal to be a lattice. Then for every ABC in A, first one, if A is less than or equal to B, then A join C is less than or equal to B join C, and A meet C is less than or equal to B meet C. Second one, A less than or equal to C and B less than or equal to C if and only if A join B is less than or equal to C. Third one, C less than or equal to A and C less than or equal to B if and only if C is less than or equal to A meet B. Fourth one, if A is less than or equal to B and C is less than or equal to D, then A join C is less than or equal to B join D and A meet C is less than or equal to B meet D. The proof of theorems 2 and 3 follows from the definitions and hence can be solved by yourself. Principle of duality. Let A less than or equal to be a partially ordered set, and let less than or equal to be a binary relation on A defined as for any elements A and B in A less than or equal to B if and only if B is less than A. Then it can be seen that A greater than or equal to is also a partially ordered set. Furthermore, if A less than or equal to is a lattice, A greater than or equal to is also a lattice, and it is denoted by A less than or equal to star. We note that both these lattices are closely related, so are the algebraic system defined by them. To be specific, the join operation of the algebraic system A less than or equal to is the meet operation of the algebraic system A less than or equal to star, and vice versa. So, given any valid statement concerning the general properties of lattices, we can obtain another valid statement by replacing less than or equal to by greater than or equal to. The join statement by replacing it with meet operation and vice versa. This is known as the principle of duality for lattices. In fact, for any A and B in A, the least upper bound of A and B in A less than or equal to is equal to the greatest lower bound of A and B in A greater than or equal to. Similarly, the greatest lower bound of A and B in A less than or equal to is equal to the least upper bound of A and B in A greater than or equal to. If A is a finite set, this property can easily be seen by examining the Hasse diagrams of the poset and its dual. Special types of lattices. An element A in a lattice A less than or equal to is called the universal upper bound if B is less than or equal to A for every B in A. If a lattice has a universal upper bound, then it is unique. Similarly, an element A in a lattice A less than or equal to is called the universal lower bound if A is less than or equal to B for every B in A. If a lattice has a universal lower bound, then it is unique. We use 0 to denote the universal lower bound and I to denote the universal upper bound. Theorem 4. Let A less than or equal to be a lattice with universal upper and lower bounds 0 and I. Then for any element A in A join I is equal to I and A meet I is equal to A. A join 0 is equal to A and A meet 0 is equal to 0. Bounded lattice. A lattice L is said to be bounded if it has a greatest element I and a least element 0. Example 7. The lattice Z plus under the partial order of divisibility as defined in example 2 is not a bounded lattice, since it has a least element the number 1 but no greatest element. Example 8. The lattice Z under the partial order is not bounded since it has neither a greatest nor a least element. Example 9. The lattice P of S of all subsets of a set S as defined in example 1 is bounded. Its greatest element is S and its least element is empty set. Theorem 5. Let L equal to the set A1, A2, etc. An be a finite lattice, then L is bounded. Proof. The greatest element of L is A1 join A2 join etc. join An, and its least element is A1 meet A2 meet etc. meet An. Next is distributive lattice. A lattice L is called distributive if for any elements A, B and C in L we have the following distributive properties. First one, A meet B join C is equal to A meet B join A meet C, and A join B meet C is equal to A join B meet A join C. If L is not distributive, it is called non-distributive. These properties can be verified in the same way as the earlier results. Example 10. For a set S, the lattice P of S is distributive since union and intersection, the join and meet respectively, each satisfy the distributive property. Example 11. The lattice shown in figure 8 is distributive, as can be seen by verifying the distributive properties for all ordered triples chosen from the elements A, B, C and D. Example 12. Show that the lattices shown in figure 9 is non-distributive. Solution. For A, we have A meet B join C is equal to A meet I, which is equal to A, while A meet B join A meet C is equal to B join 0, which is equal to B. And for the second figure, observe that A meet B join C is equal to A meet I, which is equal to A, while A meet B join A meet C is equal to 0 join 0, which is equal to 0. Now, we will see a theorem on the condition to show that a given lattice is non-distributive. Theorem 6. A lattice L is non-distributive if and only if it contains a sublattice that is isomorphic to one of the two lattices in figure 9. Complement of an element. Let L be a bounded lattice with the greatest element I and the least element 0, and let A be an element of L. An element A dash in L is called a complement of A if A join A dash is equal to I and A meet A dash is equal to 0. Observe that 0 dash is equal to I and I dash is equal to 0. Example 13. The lattice L equal to P of S is such that every element has a complement. Since if A is an element of L, then its set complement A complement has the properties A meet A complement is equal to empty set and A join A complement is equal to S. Example 14. The lattices in figure 9 each have the property that every element has the complement. The element C in both the cases has two complements A and B. Example 15. Consider the lattices D20 and D30 discussed in example 3 and which is shown in figure 4 and figure 5. Observe that every element in D30 has a complement. For example, if A equal to 5, then A complement is equal to 6. However, the elements 2 and 10 in D20 have no complements. Examples 14 and 15 show that an element A in a lattice need not have a complement, and it may have more than one complement. We will see now that for a bounded distributive lattice, the situation is more restrictive, as shown by the following theorem. Theorem 7. Let L be a bounded distributive lattice. If a complement exists, then it is unique. Proof. Let A dash and A double dash be complements of the element A in L. Then A join A dash is equal to I and A join A double dash is equal to I. Similarly, A meet A dash is equal to 0 and A meet A double dash is equal to 0. Using the distributive laws, we obtain A dash is equal to A dash join 0, which is equal to A dash join A meet A double dash, which is equal to A dash join A meet A dash join A double dash, which is equal to A join A dash meet A dash join A double dash, which is equal to I meet A dash join A double dash, which is equal to A dash join A double dash. Also, A double dash is equal to A double dash join 0, which is equal to A double dash join A meet A dash, which is equal to A double dash join A meet A double dash join A dash, is equal to A join A double dash meet A dash join A double dash, which is equal to I meet A dash join A double dash, which is equal to A dash join A double dash. Hence, A dash is equal to A double dash. Complemented lattice. A lattice L is called complemented if it is bounded and if every element in L has a complement. Example 16. The lattice L is equal to P of S is complemented. In this case, each element of L has a unique complement which can be seen directly. Example 17. The lattices shown in figure 9 are complemented. In this case, the complements are not unique. Finite Boolean algebras. In this section, we discuss a certain type of lattice that has a great many applications in computer science. We have seen in example 2 that if S is a set and L is equal to P of S and set containment is the usual relation of containment, then the poset L subset of is a lattice. These lattices have many properties that are not shared by lattices in general. For this reason, they are easier to work with and they play a more important role in various applications. Theorem 8. If S1 is equal to set x1, x2, etc. xn and S2 is equal to set y1, y2, etc. yn are any two finite sets with n elements, then the lattices P of S1, subset and P of S2, subset are isomorphic. In particular, the Hasse diagrams of these lattices may be drawn identically. The essential point of this theorem is that the lattice P of S with subset is completely determined as a poset by the number modulus of S and does not depend in any way on the nature of the elements in S. Example 18. Figure 10a and b show Hasse diagrams for the lattices P of S with set containment and P of T with set containment respectively, where S is the set ABC and T is the set 2, 3, 5. It is clear from this figure that the two lattices are isomorphic. In fact, we see that one possible isomorphism f from set S to T is given by f of set A is equal to set 2, f of set B is equal to 13, f of C is equal to set 5. F of A comma B is equal to 2, 3, f of B comma C is equal to 3, 5 and f of AC is equal to 2, 5. And f of set ABC is equal to 2, 3, 5 and f of empty set is equal to empty set. Thus, for each n equal to 0, 1, 2, 3 etc., there is only one type of lattice having the form P of S with set containment. This lattice depends only on n, not on S, and it has 2 raised to n elements. If a set S has n elements, then all subsets of S can be represented by sequences of zeros and ones of length n. We can therefore label the Hasse diagram of a lattice P of S with set containment by such sequences. The labeling in this manner by zeros and ones of the diagrams given in figure 9a and b can be seen in figure 11. If the Hasse diagram of the lattice corresponding to a set with n elements is labeled by sequences of zeros and ones of length n, then the resulting lattice is named Bn. The properties of the partial order in Bn can be described directly as follows. If x is equal to a1, a2 etc. an and y equal to b1, b2 etc. bn are two elements of Bn, then x less than or equal to y if and only if ak less than or equal to bk as numbers 0 or 1 for k equal to 1, 2, 3 etc. n, and x meet y is equal to c1, c2 etc. cn, where ck is the minimum of ak, bk, and x join y is equal to d1, d2 etc. dn, where dk is equal to the maximum of ak, bk, and x has a complement x dash which is equal to z1, z2 etc. zn, where zk is equal to 1 if xk is 0 and zk is equal to 0 if xk equal to 1. The truth of these statements can be seen by noting that Bn less than or equal to is isomorphic with P of S with set containment. So, each x and y in Bn correspond to subsets A and B of S. Then x less than or equal to y, x meet y, x join y and x dash correspond to A subset of B, A intersection B, A union B and A complement respectively. The figure 12 gives the Hasse diagrams for Bn for n equal to 0, 1, 2 and 3. The first one you can see Bn corresponding to n equal to 0, second one corresponds to n equal to 1 with two elements 0 and 1, third one corresponds to n equal to 2 and fourth one corresponds to n equal to 3. We have seen that each lattice P of S with set containment is isomorphic with Bn, where n is equal to the number of elements of S. Other lattices may also be isomorphic with one of the Bn and thus possess all the special properties that the Bn possess. Example 19. Consider the lattice D6 under the partial order of divisibility. The Hasse diagram of D6 is shown in the figure 13, and we now see that D6 is isomorphic with B2. Here, function f from D6 to B2 is an isomorphism where f of 1 is equal to 0, 0, f of 2 is equal to 1, 0, f of 3 is equal to 0, 1 and f of 6 is equal to 1, 1. Now, let us define Boolean algebra. A finite lattice is called a Boolean algebra if it is isomorphic with Bn for some non-negative integer n. Thus, each Bn is a Boolean algebra and so is each lattice P of S with set containment, where S is a finite set. Now, let us summarize the contents of this session. We have defined a lattice and seen the different properties of a lattice. We have discussed different types of lattices with various examples. Also, we have seen the important theorems in this topic. We have concluded the session by defining Boolean algebra. Here are some questions which are provided for testing yourself. First one, is the poset A equal to the set 2, 3, 6, 12, 24, 36 and 72 under the relation of divisibility a lattice. Second one, show that if a bounded lattice has 2 or more elements, then 0 is not equal to I. Third one, show that the lattice Dn is distributive for any n. Fourth one, find the complement of each element in D42. Fifth one, let S is equal to the set ABC and L is equal to power set of S. Prove that L with less than or equal to is isomorphic to D42. Sixth one, are there any Boolean algebras having 3 elements, Y or Y not? Here are some books for further reading. First one is Discrete Mathematical Structures by Coleman, Busby and Rose, Prentice Hall, Upper Saddle River, New Jersey. Second one is Discrete Mathematics and its Applications, 6th edition by Kenneth H. Rosen, McGraw Hill International Edition. Third one is Elements of Discrete Mathematics by C. L. Liu by McGraw Hill International Edition, Computer Science Series 1986. Fourth one is Discrete Mathematics by Richard Johnson Baugh, Pearson Prentice Hall 2005. And finally, Introductory Discrete Mathematics by V. K. Balakrishnan in 1991. We will continue with our discussion on Boolean algebra in the next class. Have a nice day.